All right, let's work through one of these where the degree of the top is bigger than the degree of the bottom. And if I've planned things carefully, I don't think that the denominator will just cancel out completely. So it's still going to be very valuable to go ahead and factor. I'm looking at an x plus 2, x minus 1 over x plus 3. And the reason I need to factor is that's still going to help me find my local behavior. So for local behavior, I see that I will have zeros. Remember, when the top of the fraction is 0, it makes the entire function 0. So those are your x-intercepts, and those will be at -2, because -2 makes the first factor 0, or +1, which will make the second factor 0. So we have two x-intercepts. We also have a vertical asymptote at x equals -3, and we do not have any holes in the graph. There are no factors that can cancel out, so we'll just say none. Okay, so here's where it's going to get a little more interesting. For the global behavior, since the degree of the top is bigger than the degree of the bottom, and we didn't just get to algebraically wipe that out completely, we're going to have to rewrite this fraction using long division. So the factored form was very useful for local behavior, but it doesn't help me find the global behavior. And this time, even the original form isn't really helping me find the global behavior. I can say that if I'm plugging in really, really big numbers, I'm getting 1,000,000 squared on the top. That doesn't look like a square, but it's supposed to be over 1,000,000. So I can say it's getting really big, but for this one, we want to be a little bit more exact than that. It's going to go to infinity. So if I have 1,000,000 squared over 1,000,000, that's roughly 1,000,000. If I have 1,000,000,000 squared and some stuff over 1,000,000,000 and some stuff, that's roughly 1,000,000,000. So I can see that the bigger the x I plug in, the bigger the fraction's going to be. The top wins. The fraction is dominated by its numerator. So I know the x's are going to get really big, but I want to say exactly how they're going to do it, because it's not just like a polynomial where they just kind of get steeper and steeper and steeper. They'll do it in a very specific way. So my long division, I need to divide an x plus 3 into an x squared plus x minus 2. And to make the x squared and the x match up, I'll need to multiply by x, and I'm multiplying the x plus 3. So I'll get an x squared plus 3x, and then I need to subtract and see what's left over. The x squareds get eliminated. That should always happen. Be very careful with your sign here. You get an x minus 3x, which is -2x. And then we're working with two terms. We're dividing by x plus 3, so we need two terms to line that up with. So we'll bring down our -2. So now my question becomes, what do I need to multiply x plus 3 by to match up the x and the -2x? And the answer is a -2. So I multiply that -2 by my x plus 3, and I get -2x. That should always line up. And then it's a -6. And then I want to check again and see what's left over. So the -2x's drop out. I get -2 plus 6, which is 4. So what I've just found out is a third form of my function. My function is also equal to x minus 2. I'm getting that from right here, the x minus 2. That's what I got. And then the remainder matters. We want to write that down. Plus 4 over x plus 3. So I've rewritten it now so I can see that my function is equal to a linear function, y equals x minus 2, plus this proper fraction, 4 over x plus 3. And again, the reason this is useful for global behavior is we're thinking about what happens as x gets really, really big, positive or negative. And the answer is basically the x matters the most, but the x minus 2 in general, we can include all of it because it will kind of determine the behavior. But this right here, the fraction, the 4 over x plus 3, because it's a proper fraction, that remainder term will always go to 0 as x gets big. So this is going to go to 0. So it will look like y equals x minus 2. So this is called a slant asymptote or an oblique asymptote. Try to know both of those terms because I know I sometimes switch back and forth between them. And just looking at other resources, you'll also see both oblique asymptote, slant asymptote. So y equals x minus 2. So what this is saying is, just like with a horizontal asymptote, as we head out the far left and right hand sides of our graph, our function should be starting to get close to this y equals x minus 2. And the reason for the word slant is because that does look slanted, right? We've been seeing horizontal asymptotes. Y equals x plus 2 looks like this, has a slope of 1. So our graph is going to start getting really, really close to that straight line. So let's try and put this all together and graph. Let's see. I would like to see x-intercepts at -2 and at +1. And I'm giving myself a little extra room here because with the slant asymptotes, we'll often need to have something out in the far corners of our graph. So just trying to leave a little space for myself in case that happens here. Okay, so this is x equals -3, our vertical asymptote, and then our slant asymptote is aligned with a slope of 1 and a y-intercept of -2. So that slope of 1 means I should also hit the x-axis at 2. Okay, so there's my slant asymptote, trying to make it look like a straight line. All right, so this can be a little tricky for people. What I would do is the exact same plan. It just looks a little bit different. So remember, your global behavior tells you what to do at the far left and right hand sides. So I know that I need an arrow heading out the far left and right hand sides of my graph that's pretty close to that slanted y equals x minus 2. And what I do from there is, just like before, I'm going to start to drift away from that line as my local behavior takes over. So as I'm moving left to right, my first piece of local behavior is this vertical asymptote at x equals -3. So I have two choices. I can either turn around and head down to -infinity, or I can creep up and head to +infinity. And I can eliminate that option, that second option, because I don't have an x-intercept anywhere to the left of x equals -3. So I'm not allowed to cross. So I'm probably starting just below that line. Again, they can cross through those, so it's not the end of the world, but more often you'll see them just stay below. And then I have to just turn around and head to -infinity. So this is one of those where if you graph with technology, it's really easy for that to be a little too low and not fit into your graph. So it's very important that you realize that there should be something there. And just like we talked about before, I really can say for this function that the domain is x does not equal -3, which means you better have something going on for every x value besides -3. However, once these get slanted, sometimes people are tempted to do things like put something above and below the slant asymptote. Do remember that yes, you want to represent every x value, but you don't want to represent it twice. If your graph ends up not passing a vertical line test, you've done something wrong, because these are functions. So these should pass vertical line tests. Okay, everything I was working with had powers of 1, multiplicity 1. So that means that every time I pass by an intercept or a vertical asymptote, my signs change. So if I was headed to -infinity on the left-hand side of that asymptote, I'm going to head to +infinity on the right-hand side. The next thing I need to do is get to my x-intercept at -2, and I'm going to cross right through because that's multiplicity 1. And then the next thing that takes over is another x-intercept. Again, it's totally fine in the middle of this graph for you to just ignore that slant asymptote. So sometimes you will see these come and cross through their slant asymptote, and then maybe they'll approach from below. So don't panic if you have to cross that slant asymptote. The only one you shouldn't be crossing is the vertical, because it's actually representing a domain problem. But here, it looks pretty likely to me that I probably turn around and come back up and cross through at 1 and don't actually have to cross through that slant asymptote. And now all that's left over is that global behavior, so I won't have to worry about anything else except for getting close to y equals x minus 2. So this is one of the things you can see where it looks like we took our parent function and we just picked up this horizontal asymptote and we tipped it, and it kind of smushed our graph in. So this is one of the things that you might see. The other thing that can happen is we could tip the other direction, and you might end up with this kind of long flattened out version where instead of scrunching and making those two branches of our parent function look a little scrunched, they actually look a little stretched out because maybe we visualize tipping the other way, right? So these will actually get bigger instead of smaller. And again, things can be upside down. There can be all variations, but that's how I kind of look at how is this still related to that parent function. Okay, so we'll see both of those, but hopefully that gets you a good start.